So this lesson is all about the relationship between polygons and angles. And so in order to start talking about this, we first have to understand what a polygon is. And to do this, I'm going to show you some examples of polygons, and then some examples of things that are not polygons. We're going to try to come up with some characteristics that are shared by the ones that are, but not shared by the ones that aren't. Now, of course, we can say that any polygon is a type of shape that we are familiar with. Polygons, for example, are squares. Um, Squares are polygons. Triangles are polygons. Other shapes like pentagons are polygons. Um, Hexagons are polygons, etc., etc. But some other polygons that you might not have thought about a lot, but are also polygons other than the triangle, diamond, and hexagon that we see here are things like a star. A star qualifies as a polygon. Also, this arrow qualifies as a polygon. So now with all of these in mind, let's take a look at some things that are not polygons. This half circle is not a polygon, neither is this oval. And they share the same reason for not being a polygon. This hourglass looking thing here is not a polygon. As you can see, the sides go down. It's like someone drew a very cornered figure eight. And this little arrow here is also not a polygon. So we want to look at the polygons to the left and the non-polygons to the right and see what characteristics they share or they don't. Go ahead and pause the video and see if you can come up with a few characteristics that are shared by the polygons but not by the non-polygons. Well, when I said that the half circle and oval share the same reason for not being a polygon, what you might have noticed is that they both have this curved edge. The oval is entirely curved, but the half circle is curved in its top half. And we notice that none of the polygons on the left-hand side have a curved edge. You might also notice that there is a cross in the hourglass that is not shared by any of the polygons on the right-hand side, and that each of the polygons on the left-hand side, each of the polygons is complete and there are no breaks like there are in this arrow figure here. And for that reason, it is not a polygon. And those three characteristics are actually the three principal characteristics of a polygon. First, it is closed, meaning that there are no breaks in its lines. Second is it is made of line segments, which means it cannot be curved because line segments are straight. And finally, none of the segments intersect except at endpoints, meaning there are no crosses anywhere in the polygon like there are in this hourglass right at the center. So an example of something that is not closed is not a polygon, something with curved edges is not a polygon, and something with a cross like this is not a polygon, in that this one edge here crosses another. And so when we have polygons, we get into the idea of naming polygons. And all three-sided polygons, as we're familiar with, are called triangles. All four-sided polygons go by the name quadrilateral, although there are many different types of quadrilaterals and many different types of triangles. But from here on out, for the rest of the polygons, we start naming them with a word ending in gon. Pentagon. Penta meaning 5, gon for polygon. Hexagon. Hex meaning 6, gon for polygon. And so on and so forth through the heptagon, octagon, nonagon, decagon. And then we're going to skip one for a second. We're going to go to a dodecagon, which has 12 sides, which is more common than the 11-sided figure. And also for 20 sides, we have what's called an icosagon. I want to go back through these slides one more time, and I want you to notice how the shape changes from a pentagon to a hexagon, a heptagon to an octagon, a nonagon to a decagon, a dodecagon, and finally an icosagon. And as the sides get smaller and there are more sides, it seems to approach. It actually looks like it's becoming more and more circular. But there are still tiny edges there. If it were truly circular, it wouldn't be a polygon. But there are actually 20 of these tiny edges all the way around the icosagon. And so there are special types of polygons, and we know that this is true for triangles and quadrilaterals because we've named special types of them, but there are special types of polygons where you can have a shape in that type of gon where all angle measures are equal and all side lengths are equal. Something like a square for the quadrilaterals and an equilateral triangle for the triangles. And these generally, where all the sides are the same and all angle measures are the same, go by a special name called regular polygons. And there is a regular polygon for every type of shape. If you look down through these shapes that were shown here, triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, you'll notice that all of the sides are the same length and all of the angles are the same measure. And so I want to look at a few of those polygons now and try to figure out how many degrees there are in each of those. And we're going to start with a square because we're familiar with the idea that all quadrilaterals have 365 degrees. So if we take a look here and draw a line, we can see why all quadrilaterals have 360 degrees. Here we've split this square into two triangles. Now both triangles, their angles, form an angle of the square. Even though they may share an angle with the other triangle, they both form an angle of the square. So if we have 180 degrees in this triangle and 180 degrees in this triangle, and all of their angles form some angle of the square, that means the square must have the total of the angles, 360 degrees. And indeed, it does. And now if we do that for a pentagon, what we're going to do is we're only going to choose one vertex. And we're going to draw what are called diagonals. Diagonals are lines from one vertex to another that are not already included as edges of the shape. And now this splits the pentagon into three triangles. And we chose only diagonals from one side because it is important to recognize that these diagonals, every corner, every angle of each of these triangles forms or helps to form part of an angle in the pentagon. We only want angles that are part of the actual pentagon. And now there are three triangles here, and if we add up 180 degrees from every triangle, we end up with 540 degrees. Now see if you can pause the video and see if you can figure out how we would do that with the hexagon. Remember, we're going to choose one vertex and only draw diagonals from that vertex to every other vertex that it doesn't already have a connection with. Pause the video and see how many degrees you think are in a regular hexagon. Well, if you take one vertex, let's take the vertex here, and draw a diagonal to each vertex that it has already connected with, you have 1, 2, 3, 4 triangles, and 4 times 180 is 720 degrees. And what that gives us, because when we look at all three polygons that we use, we can see this is 180 times 2, and there are 4 sides. This is 180 times 3, and there are 5 sides. This is 180 times 4, and there are 6 sides. And in general, that is true. For a polygon of any number of sides, we say that generically as n sides, and we call that an n-gon, to represent that it has that many sides. The sum of the measures of all the angles is just 180 times 2 times the number of sides it has minus 2. And why is it minus 2? Because this one vertex that we already chose is already connected to 2 sides. At most 2 sides, it turns out. And so the number of sides and vertices are actually connected to 2 vertices. And so the number of 2 vertices that is remaining for it to connect to is the number of sides minus 3. It connects then, it creates then n minus 2 triangles, and each triangle has 180 degrees. And so remember, n is just the number of sides in that polygon. So see what you can do with all of these examples. These are examples of regular polygons. And we're going to use the formula that we saw before, which is subtract 2 from the sides and multiply by 180, and you will find out the number of degrees in each of those polygons. So go ahead, pause the video, and see what you can do with it now. Well, let's start with the first one, which is a nonagon. 9 sides. So n equals 9. 9 minus 2 is 7, so 7 times 180 will give us the final number of degrees in the nonagon, which is 1,260. So in a single nonagon, a nine-sided figure, there are 1,260 degrees. In number 2, we have a 15gon, one with 15 sides, and we could call it a pentadecagon, but it's much easier to call it just a 15gon. So in this case, n is equal to 15. 15 minus 2 is 13, so 13 is what we're looking at. 13 times 180, because that is the formula, gives us a total of 2,340 degrees in a 15-sided shape. And so now looking at number 3, the icosagon, we can see that in that case we have n is equal to 18, or excuse me, n is equal to 20. When we subtract 2, we get 18. 18 times 180 will give us the number of degrees in an icosagon, and it turns out that any icosagon has 3,240 degrees. Finally, we're looking at a 102gon, or 102gon, in number 4. N equals to 102. N minus 2 equals 100, and so 100 times 180 means that in any 102gon there are 18,000 degrees. And so that leaves us with another question, is if we know the number of degrees in a regular polygon, can we find the measure of individual angles in that polygon? And if we can, how can we find it? We know the number of angles, and we know the total sum of the degrees. So how can we use that information to find the measure of an individual angle? And as a quick review, the number of angles in any regular polygon is just n minus 2, where n is the number of sides, times 100.